Well, what fun would chemistry be without stoichiometry, right? So we're now going to apply what we learned before about the enthalpy of a reaction to stoichiometry. So specifically, in a combustion reaction, for example, if you burn a certain amount of fuel, how much energy can you expect to get out of that amount of fuel is the kind of problem we're going to be looking at. In the last video, we did a problem where we had the combustion of ethanol, and we found the change in enthalpy for that reaction, and we discovered that that change in enthalpy was a negative 1234.7 kilojoules. Okay, we did that in the last one. Now, the best way to think about this is if this is negative, that means the reaction is exothermic, so that means it is giving off heat. So therefore, I can take this heat and I can actually put it as a product in my reaction. So I'm going to come over here and I'm going to add 1234.7 kilojoules to the reaction on this side, because don't let the change in negative sign confuse you, because we're giving off carbon dioxide, we're giving off gaseous water, and we're giving off heat. So therefore, because we're giving off heat, this now has gone from a negative number to a positive number, and it goes on the product side because that's a product of a combustion reaction, is a lot of heat. So I'm actually going to put that on the product side of my reaction. And then if you look at the sample problem that we're working, I said how much energy can be produced by burning 150 grams of ethyl alcohol in excess oxygen. So if the oxygen is excess, which is normally the case in a combustion reaction, this is going to be our limiting reactant. And so I know that I have 150 grams of C2H6O. That's what I'm starting with, and I want to know how much energy is going to be given off. Well, just like in any stoichiometry reaction, I have to convert grams to moles. So 1 mole of C2H6O, 1 mole of ethanol. I have 2 carbons at approximately 12 apiece. I have 6 hydrogens at 1 apiece. I have an oxygen at 16. And so that gives me a total of 46.08 grams of ethanol for every mole. Okay, so my grams will cancel out, and that will be left with moles. Now, what I know from my balanced equation is that for every 1 mole of ethanol, and I need to put that on the bottom so that it will cancel, I'm going to produce 1234.7 kilojoules of energy. So that goes on the top. So moles of ethanol will cancel out, and I will be left with kilojoules. So 150 divided by 46.08 times 1234.7 will give me 4,019 kilojoules of energy that are given off in this reaction from the initial 150 grams of ethanol. Okay, so that's what it looks like for an exothermic reaction. Now let's look at an endothermic reaction. So if you look at the second example problem that I gave you, it says one way of producing butane, which is C4H10 for cigarette lighters, is to force ethane to react with itself. If you have 1.23 kilograms of ethane and would like to turn it all into butane, how many kilojoules of energy would be necessary? And I believe I told you there that the reaction requires 43, or the delta H for the reaction is 43 kilojoules. So what we need to do is get this balanced equation first. Tell you what, let's make a little bit more space here. This is a little easier for you guys to see. Okay, so my reaction is 2C2H6, which will react with itself to form C4H10. H10 with some leftover hydrogen gas. Okay, and I told you that delta H is positive 43 kilojoules. So this is positive, so what that means is it's endothermic, and so that means the energy has to be absorbed by the reaction in order to make it run. So in this case, the 43 kilojoules, we will add that as a reactant, whereas before, when it was exothermic, I added it as a product, okay? So that's the only difference here. Now, it says that I had 1.23 kilograms. If I'm going to convert it to moles, I've got to convert that to grams. Well, 1.23 kilograms is the same as 1,230 grams of C2H6 over 1. And just like before, I am going to convert that to moles. In 1 mole of C2H6, I have 30.08 grams of C2H6. So my grams will cancel. And in this particular reaction, I have 2 moles of C2H6 because that's what my coefficients tell me. And for every 2 moles of that, I require 43 kilojoules. So moles of C2H6 will cancel. And then when I crunch all those numbers together, I end up with 880 kilojoules of energy that are required for this particular reaction. So just to kind of sum things up here, if you have an exothermic reaction, the delta H amount of change in enthalpy is going to go on the product side. If you have an endothermic reaction, the amount of energy that you calculate in your delta H is going to go on the reactant side. So when you do that, you will then be able to calculate either in an exothermic reaction how much energy is produced, or in an endothermic reaction how much energy is required for that reaction to run.